can see the problem here. So it turns out the problem was correctly worded, it's just really awkward. I would never write it this way. But did you did get this one finally, right? A?
Yeah, I got it finally. So, oh my God.
Yeah, but all of you spent a lot of time on this problem, I hear. I don't need to explain this anymore. It turns out every other such road, that's where the misunderstanding was for most people and for me. What can I say? However, to their credit, the example was right. It did take care of this strange case where I was going, this is the second line, why is the 3 on this side? But anyway, overall, that was one of the more annoying ones, and that to put it in A really ended up messing a lot of people. If it had come later, maybe you would have somehow managed it. But that's what life is.
But for some reason, I understood the first time I read it.
Yeah?
Yeah.
Yeah, well, obviously many people did, because they solved it in 3 minutes.
Oh, you
Yeah.
have sold
Yeah.
it super fast.
Yeah.
You sold it
Yeah,
super fast.
so and if you look at the problem, if you look at the solution, it is really easy.
Yeah.
It says if the row is balanced, meaning if the amount of gap is even, then don't worry about it. Just put it in the center and move on. If it is not, then keep count of it and process all the well, sorry, this is the one for the balanced rows. For the unbalanced ones, just alternate extra space between left and right. That's it. Nothing fancy there. It's a linear time algorithm, very simple. So it's not surprising people got it, were able to do it in 3 minutes, but to understand it and then do it sounds. I am not happy with that. Okay, so let's talk about problem B. How many of you got this one? You did. Okay, good. So good. B is fairly easy. Where's my? I have to get under this one. Sorry. Okay. How many of you read this problem? No? All right, read it now then. I didn't know 2024 was a perfect square. Oh, 2024 is not a square. Okay, it's just the size of the side. Okay, got it. So Brandon is given a square of side 2024, right? And then he's allowed to draw additional line segments so that the square starts to have various partitions. But he has to add extra line segments in order to do what?
To create the minimum amount of.
To make triangles.
To create triangles.
To create only triangles in the square, right?
Yeah.
Every little area in the square, after you've drawn additional line segments, should only be triangles, and he has to draw the minimum number of segments. That's all the problem. Fine. So the input, you're given the square, of course, and you're given one extra line segment. Okay. So in the first case, he's given a 2024 by 2024 triangle, sorry, square, and then there's one line segment that goes from 0, 10 to 10, 0. Yeah? So this one line segment cuts this little corner on the bottom side. And this says that he needs 2 extra line segments in order to make this happen. And we can actually work that out here. It's quite simple, but actually I may actually have pictures. So let's just do it here. Okay. So you're given. So this is the 2024 by 2024 side, right, square, and then he's given a second line segment that goes something like that. 0, 10 to 10, 0. Fine. So how do I add minimum number of segments so that you have the least so that you only have triangles left? It turns out you just do that. Okay, that's the first example. The second example says we're given a 2024 by 2024 square, and the extra line segment that's given goes from 0, 0 to 2024 all the way across. So it goes like that. And the answer tells you that you don't need to add any more because already the square is broken into triangles. Is that clear? So those are the 2 examples, and from here you're supposed to take care of the rest. So how do you do this? And what are the cases that you have to worry about?
There's another one where it can be touching one of the sides and one of the corners.
That's right. So it's possible that you have a corner and a side. So let me draw that here. So you could have something like that. Let me draw one more here because you need a general case. So you're saying something like that, right?
Yeah.
And then is that a 4th case? Well, what is the answer for that, and what is there, does it cover all the cases?
There
Yes?
could be a straight line
Yeah.
forming 2 squares.
Well, it's already a square, you mean 2 rectangles? What are you talking about?
Yeah.
Nothing needs to be horizontal or vertical, so what's the general case over here?
Even if or from like one side
Right.
to another side. That's not
Side
gonna
to
happen
other
actually.
side. That's right. Okay, something like that. So these are the 4 cases that we need to consider. This guy takes care of the case when the line segment you're given connects 2 adjacent sides. Here you have 2 opposite sides. Here you have 2 corners. Here you have 1 corner and 1 of the sides. There are no other possibilities. Is that clear? So let's figure out the answer for each of the cases. So remember, in this case, it was that. Those are the 2 line segments to be added, so the answer was 2. Here it goes 0. What is it here?
1.
Which is, what do you do?
Put it to the other corner.
That's right, so you do that, right? And the answer is 1. Is that clear? What do you think it's here?
2.
And again, you do that and you do that. Right? Did I miss any cases here? Well, theoretically, you could have a line segment that's parallel to this. I don't know if the problem disallows that, but if it doesn't, then you will need at least one line segment to take care of this, right? Any questions about this? All good? Too easy? It's not too difficult to write down the cases that are needed, but still the coding may involve, to write it compactly will require some skill, but you don't have to worry about, since you don't have to worry about having some extra lines, you could just make up all the possible cases. It's possible that the edge case it's between this side and this side, or between this side and this side, or between this side and this side, or between that side and that side. You may end up writing 4 cases separately, or you could just figure out for any line segment that touches 2 adjacent sides, write some piece of code that figures out what the opposite vertex is, right? So that takes care of B. And you're coming in right when I finished all the easy
I'm so
problems,
sorry.
and now we get to the hard problems so that you can help us.
Oh, wow.
Okay. So the next problem, I have something on, I think it's,
I have extra copies in the office. Did you want some? The extra
Sorry?
copies of this.
well, only Ian has not seen this before. Did you want an extra copy? She can.
Sure.
Okay, I'll go get it.
Thank you.
Sure.
Yeah, animated rails. So again, it's Brandon who's back, interested in trains. Who did not try this? Did anybody try this? You said you kind of figured this out, right?
Yeah.
Alejandro
I did
tried
already.
You
it,
did try
but
it?
he couldn't.
Okay, so, but please read this, yeah, I'll give you a few minutes to read it so that we can talk. Okay, so what is the problem? The problem says that there are 3 islands and need to connect, there are railway tracks, there's a railway network on each of the islands. But now, they're trying to build connections between the islands. And the question that's being asked is what? Oh wow, that's a lot.
Which division?
I think they all have the same problems, right? Did they both have the same problems?
I think they differed by like a few, but
Sorry?
I don't think they're exactly the same,
No?
but they're mostly similar.
Oh, this one is.
Sorry? Well, it says division two, but I'll take my calculator and do this.
One has the same problem.
Oh, this is different.
Sorry?
It's different.
It's different?
Yes.
Division 1E is this.
This E, is E there?
Here is a different problem. Which one is one?
Oh, okay, then you
So
better
then
take that.
It's division 1.
Okay, there are only 5 copies, so, and there's 7 here.
No, I
You have that?
the
This
right.
one.
Here,
No, no, Lorena gave you division 2. Check
Yeah,
that.
that's division 2.
This is
Okay.
division 2.
We both have it, so.
Okay.
Oh, yeah, you can.
Yeah, here,
What do I do?
I have the region.
you have division
I'm
1.
gonna put it on.
Sorry?
I'm gonna put this on.
Okay. Any of you? One? 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 This one? Oh, you got it, okay. Here. Okay. So, what is the problem asking us?
So it wants us to put the maximum number of stations that could appear on a path between two stations that we get as input.
Right. Okay, so again, it's easiest to understand with one of the examples, so let's just go through the example here. Yeah, here's the first example. It says that n is 12. So that means that there are 12 connections. And what is 3? I forgot.
The number of queries.
Oh, the number of queries, that's right. Yeah. So 12 is actually
Number
the
of
number of
stations.
stations, not connections, and 3 is the number of queries. So these 3 are the queries, and everything until there are the so the first. Okay. I'm missing something. Okay, so n minus 3 lines each contain 2 integers x and y, indicating the stations x and y that are connected. You always have only 3 queries?
No.
Why is it n minus 3 lines?
If you scroll up, they guarantee that for any pair of stations on an island, there's exactly one way to get from one station to another. So
Right.
that means that each island actually ends up being a tree.
Okay, oh, that's right.
Yeah.
Of course, yeah. All right, good. Very good. So, so it says that 1 is connected to 2, and because there's a connection, they must be on the same island. Now we'll just put that over here. 1 to 2. And then we have 2 to 3. And then we have 2 to 4. Okay? Then we have 5 to 6, and then it doesn't show up afterwards, so let's say 5 to 6 is over here. Okay? And then the rest of the edges are on the third island, goes from 8 to 9, 9 to 10, 9 to 11, 8 to 9, nine to 10, I think it's 9 to 11, right?
Yeah.
And then we
11
have
to 12 and 7 to
11
8.
to 12. Oh. And then 7 to 8. this is what's given to you. Right? And now your three queries are, use a different pen, 2 comma 5, 11 comma 4, and 7 comma 6. Okay. So 2 comma 5 is you'd like to get from here to here. And you want to know what's the maximum number of stations you can touch along the way. So the general idea is all your queries involve 2 vertices, 2 stations on different islands. So you want to travel as much as possible on this island. You want to travel as much as possible on this island, and then you also want to touch the 3rd island and visit as many stations over here as possible. That's the general idea. So therefore, for the first one, 2 to 5, you could either go to 2 to 1, 2 to 3, or 2 to 4. They're all exactly the same length. So let's say we take 2 to 4, and then we want to traverse as much of this island as possible. So we could go from 4 to 7, and then go all the way to 12, and then go from 12 to the other island. In this case, you would go to 6, and then make your way to 5.
Yeah.
Okay, so that would give you 1. Well, you're counting the number of stations, so it's actually 1, 2, 3, 4, 5, 6, 7, 8, 9. So the number of stations that the maximum number of stations you can visit is 9. There is no way to visit all the vertices here because depending on where you go, there's a unique path within the connections on this island. Is that clear? So that gives you 9, and that's what this answer tells you. The second one is from 11 to 4. Let's change color. So you want to go from 11 to 4. Again, the general idea is you want to travel as much as possible within this island, as much as possible within that island, and then cover in the middle, also visit the 3rd island and cover as much of that as possible. So in order to traverse the most within this island, you pick the farthest vertex from 11, right? In this case, that would be 7, right? Clear? And then from 7, you would jump to this island, cover everything there, or as much as possible over there. And now you want to go to 4, but you don't want to go directly to 4. You want to go as far away from 4 as possible, and then traverse as many stations as possible on that one. So you go from here to, from here you go to 1, and then make your way to 4. Is that clear? So you would go to 1, 2, 3, 4, 5, 6, 7, 8, 9. And so you get 9 stations for this query. Everyone okay with this? And the third query is from 7 to 6. Again, let's use a different color. So we want to go from 7 to 6. So our job is to traverse as much as possible here, as much as possible here, and cover as much as we can over there. So from 7, where would you go?
12.
12 is the farthest, so that's what you're going to do. And then sorry, not that.
7, 12,
Then you have to go to that island, and in order to cover as much as possible of that island, you pick something, it really doesn't matter. Let's say we pick 3 here, and then we do that, and then from here, we're going to go to 5 and then to 6. right? So you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And therefore the answer here is 10. Okay? So the general strategy is very simple. There are only 3 islands. Your source vertex is on one island, your destination vertex is on another island, and then there's a third island that you should visit if you want to maximize the number of stations you touch. So what we're going to do is since the queries can be a large number, I think we're told that, what are we told?
10 to the 5 stations.
10 to the 5 stations. So n can be as bad as 10 to the 5. And then
Like 2
Q, right?
Yeah.
Yeah, Q.
Q is
2 times 10 to the 5.
also roughly of the same order. Now, the moment you see this, you know immediately that n times q is not a good idea to use for your algorithm. You want to try and do this with something that doesn't multiply n and q, right? So what we're going to do is, because there's only a small number of islands, we're going to try and pre-process the islands so that regardless of where your queries end up, we can answer the queries quite quickly, right? So the question is, what do we do with each of the islands? Now, the island could be a source or a destination, and they are treated somewhat the same way, or the island could be that intermediate island, which is treated slightly differently, because there you could come in wherever you want and go out wherever you want. Whereas the start one, you have to start from anywhere in that island and then go as far as you can. So there are 2 different kinds of problems here, and we have to take care of both these cases, which is what we are going to do. So back to the slides here. Let me see if I can help you make sense out of this. So really, we essentially have 3 islands, and in each of these islands there is a tree of connections. Now, why is it a tree?
Each node is connected to, there is a path that connects all of the nodes.
Why does it have to be a tree? I could do it with, I could connect it in many other ways. Sorry?
No cycles?
How do you know there are no cycles? So this is where that critical sentence is necessary, which is?
They tell you at the beginning that on any island there's exactly one path between any 2 stations.
That's right. So if you're told that between any 2 vertices there's a unique path, the only way to achieve this is with a tree. If you have even one extra edge, you're going to end up with a cycle. If you have a cycle, in order to get from point A to point B on the cycle, I could go this way or this way. And with the tree, I don't have that choice. There's only one way to get there. So therefore, it's something they don't tell you explicitly. You kind of have to figure this out. So you have to know that within each of these islands, what you have is a tree. So that means all our operations are with trees, and the computations end up getting to be a little bit easier than what we need. So we are starting with 3 trees because we have 3 islands. We're going to pre-process all 3 trees so that any questions about them we can answer quickly. Remember, there are going to be lots of queries. The queries could be about any of the vertices, and anytime you see lots of queries, you should know that there needs to be some pre-processing so that the queries can be handled as quickly as possible. And here the question is, what are those queries? And once we understand this, we can figure this out quite quickly. So what we're going to do is to is to find the longest path in each of these trees. Okay, now why do we need that? Well, maximizing,
the route that you take from one train
but
station to
when
another.
will you need this particular?
When you're passing through the island that's
Yeah.
neither
That's
the
right,
source.
so
or
when
destination.
only for the middle island
middle
on your
island.
path, not the source island, not the destination island, but the intermediate island, you're gonna need this particular one. Since we don't know which island is going to end up being that intermediate one, we'll just pre-compute it for all three trees. And we'll talk about how this is done, but essentially we have to find the longest possible path in any of these trees. So for that, we'll solve this problem of what's called as the longest path, or also called the diameter of the tree, and we'll see how that goes. Then we're going to need one more little tool that says, if I give you a source, if let's say I tell you that this is my source, if number 9 is my source, then I have to know what's the farthest I can go within that island before I jump off, right? So that means from every node in the tree, I want what? I want the farthest leaf, in fact, or farthest node in that tree. This is another thing that I have to figure out. So for each tree, I'm also going to figure out the farthest node within that same tree. And so this also I'm going to pre-compute. I'm going to pre-compute for every vertex in each of the three trees. So now I'm armed with all this information, and it turns out that the queries are now really, really easy to process. Remember, every query has a source tree. We'll just call it A. Every query has a destination tree. We'll call that B. And there's a third tree. We'll just call that the other tree, or the intermediate tree, and we'll call that C. So once you have this information, if the query is from vertex U to vertex V, then all we're going to do is report this following. If the query goes from U to V, I need R of U, which is the farthest I can go in the source island. R of V, which is the farthest I can go on the destination island, and that's the longest path in the intermediate island. And all three have been pre-computed, so I can do all of this in constant time. So for every query, the only job I have to do is to figure out where the heck U is and where the heck V is and what the third island is going to be. And by the way, that part of figuring out which island it's on is also fairly easy. A simple array will take care of it. Is this clear? So the key here is to pre-compute a heck of a lot of stuff which you're going to use later on in the queries. And because it's a query format, this pre-computation is what is going to save you. If you don't, then you have to compute for every query, you have to compute from scratch. So remember, there are n nodes, 3 trees put together, and there are there are queries, and so the time will end up being n times q, and that's too expensive. That becomes 10 to the 10. So that's the only key thing that you have to understand. You have to make sure n doesn't multiply q somewhere in this computation, in the time complexity. And so we end up separating out the pre-computation where we've done a lot of useful things, and we then tackle the queries very, very quickly. Is this clear? So what is left here? What is left is to tackle some of the hard parts within the algorithm. The hard part turns out to be these two steps here. How do we find the longest path in the tree? And how do we find the longest path from any given vertex within that tree? Okay, so these two are non-trivial computations, and that's what I'm going to talk about next. Are there any questions? Everything good here? So needless to say, if we do it this way, and if those two bullet points are handled in linear time, the whole thing can be done in linear time. Okay? All right, so our first step is to compute the diameter of the tree. So you're given a tree, and your job is to find the farthest pair of vertices in that tree, also called the diameter. There are many ways to do this. Mine's a little old-fashioned, so I'm going to tell you the way I think about it. I am sure if you search around, you'll find much better ways to do it than the one that I'm going to tell you now. This helps me because for me, that's how my brain works. Okay. So what do we have here? Well, the first thing is I'm given some strange-looking tree, like the one here. I have 7, 8, 9, 10, 11, and then 12. This is what I was given. I'm going to get something strange like this for an arbitrary tree. Okay. So in this tree, my job is to figure out what's the longest path. Now, when you're given the tree, it's going to be given in pieces. You're just going to get a list of edges. By the way, before you even get here, you have to first identify the 3 trees. So you have to run this connected components algorithm to separate out the 3 trees. I'm assuming that all that is somewhat easy for you guys, and you can handle that separately. I should have added it to the bullets in the previous slide. So the first thing I'm going to do is to direct the tree edges, essentially making it a rooted tree. Right now, this is what's called as an unrooted tree. There is no root, there's no parent-child relationship, there's just a tree. So our first step is going to be to make this into a directed tree. Now you can pick whatever you want as the root of the tree. In this case, let's say just to make things a little more interesting, let's make 8 the root of the tree. Okay. If 8 is the root of the tree, then this edge is going to be directed that way, right, from parent to child. So is this. It's going to go this way, this is going to go this way, this is going to go that way, and that's going to go that way. So that's my tree. Essentially, I'm holding it here and pulling it up. Fine? So my tree looks something like this. I have 8, and then I have 7, then I have 9, and then from 9 I have 10, 11, and then 12. So that's what my tree ends up looking like. Simple. And this will actually come up automatically if you do some kind of depth first search or breadth first search. Essentially, if you do depth first search or breadth first search from 8, all the new vertices that you end up visiting will become children of the vertex from which you're visiting. Okay. From 8, you're going to visit 7 and 9. They become 8's children. From 9, you're going to visit 10 and 11. They become 9's children, and so on and so forth. So simple depth first search gives you this. What's next? The next, the way I look at this is to traverse this tree in pre-order. Pre-order is something you've seen back in your second programming class or something like that. It's a way of first traversing the children, the left child first, the right child next, and then the pre-order. So this says traverse the tree in pre-order and label each of the directed edges by its distance from the farthest leaf in that subtree. So we're going to treat this as a tree, and we're going to label them in a strange way. Essentially, we're going to say how far away from the leaf in that subtree it is. So, and it's all going to happen. It's all going to happen bottom up. So if I look at 12, 12 is the root of a subtree which has nothing else. So therefore, the distance to the farthest leaf in the subtree is of length 0. Right? Well, actually, I'm not labeling the vertices. It says that I should label the edges. So I can think of labeling this edge by 1. It says that with this one edge, I can get to a leaf. So I'm going to label this as 2, this as 1, and this as 1 because these two are essentially leaves. And this one here, because this edge is at distance 1, this is going to be at distance 2. Is that clear? So what's the label over here? It's going to be 3 because I have 2 here, I have 1 here. It's going to be 1 more than the largest, right? So easy calculation. So by doing a pre-ordered traversal, once I've taken care of the children, I would have that information and I can process this. So I'm going to process the tree bottom up, and the label of edge UV is going to be the label well, I label 1 if it's a leaf, and otherwise I take the maximum of the labels of the edges going out and add 1 to it. Fine? So this kind of helps me. It's not quite the answer that I need. This is only labeling the edges. It's not labeling the vertices. I have to do a little more finish this. But it's mostly done now. We'll see. So now I'm going to add labels to the vertices, and there. Different color. Okay, so now it says define the subtree diameter, which tells you what's the longest path in the subtree. Okay, so if I look at a leaf, there is no subtree, so the longest path there is of length 0, right? So all the leaves will have subtree diameter to be 0. Fine? Something like that only has 1 child, so the longest path in the subtree is going to be essentially the same as 1, because that's the length of the longest path. Right? Now what about here? Well, the length of the longest path that's completely in the subtree, there's a path of length 2 this way, and there's a path of length 1 that way, so it's going to be 2 plus 1. Is that clear? So this here is going to get a number of 3, because here's a subtree, here's a path that's completely within the subtree and is of great distance. Here I got 1 on this side and 3 on this side, so the longest path that contains this vertex and that's completely in its subtree is of length 4. All right? We're now more or less done trying to figure out the actual diameter of the tree. Now, think about any diameter of the tree. A diametric path in the tree, if you put it on the tree, somewhere on that path, you're going to be at the highest point in the tree. Right? It's going to go up, 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 and then it's going to go down, down, down. So at some point it's at the top of the tree, and that node is going to be one of the guys that's labeled. And it's going to have a subtree diameter that's exactly the diameter of the tree. So therefore, the real diameter is one of the subtree diameters, and it's the largest one. So you just take the largest subtree diameter, and that's your diameter of the tree. And in this case, it's going to be 4. So, we're kind of figured out what is the diameter of the tree by doing this process. And so well, this tells you what to do at every level in the tree, right? And then finally, the diameter of the tree, I will simply take that to be the largest one, and I'm done. So whichever is largest, that's the diameter of the tree. The vertex maximum subtree diameter is also the diameter of the tree. So this is my way of doing it. As I said, there are many ways to handle this. Okay. All we did here was to process things in such a way that only the subtrees are given to you. And the only main tricky step here is, as you finish the tree, when you get to a certain vertex, there may be many subtrees here. Each subtree will give you a longest path, right? This longest path could be L1, this one could be L2, L3, Lk. In order to find the longest path that goes through this vertex and it stays within the subtree completely, you just take the two largest ones and add them up. So if L1 and L2 are the two largest ones, it's just going to be L1 plus L2. Is that clear? Well, you have to add one in because you want the number of vertices. You only added the edges. Everyone okay with this? So this is a simple trick for me. It's a simpler way to think about diameters. You process things going up, bottom up in the tree, and in the process you end up with the subtree diameters. And we're more or less done with this. Essentially, this method also helps you to find what's called as the central vertex. There is something called the center of the tree. There are other algorithms where you need this. Center of the tree is it's the center of the diametric path. Okay, it's the vertex from which your farthest vertex is as close as possible. Okay, because in the center of a circle, it's the point where the farthest guys are as close as possible, right? You don't want it to be farther away on this side and less far over here. So then you would end up moving the center a little bit. So if I want to find the center, you have any thoughts on how I would do it with the structure I have?
You're talking about the center, like in an island?
In an
Would it be
island,
the
correct.
midpoint of the longest
Center
path?
of a tree. How do I find the center of a tree?
Would it be the midpoint of the longest path?
That's right. So you just find the diametric path, and we just found it, and we find the middle point of that path. So in this case, how would I find it? Let's say I've done all this work, and I found the longest path, and I know that the longest path is of length 4. Now, how do I find my center?
Find paths for 2.
Sorry?
Find stations that have a path of 2 from.
I guess you could do that.
Is that why you said you couldn't?
That's not good enough because we don't know if that's going to be on that diametric path. So you have to be a little bit more careful,
Okay.
right? So here, you need to, you can actually locate the diametric path, right? The diametric path here is this one that leads to 1. And then you need something that's of length 3 here, and that's this guy here, right? And now you have a path of length 5, and so therefore the center is that one there. Does that make sense? So as you do the maximum, you can keep track of which side gave you the largest one, and then you would know where and if you follow back that path, you can figure out where the center is. So you have to put in a little extra work if you want to actually find the center. Now, finding the center is useful for various reasons, because it turns out to be useful for the next part of the tree. So this whole thing runs in linear time, because all we did was do depth first search or breadth first search on a tree, which has only linear number of vertices and edges. Are you clear about that? Everyone okay with this?
Why'd you put 2 question mark?
Where?
Central vertex 2?
Yeah, so that's a little trick that you have to worry about. In general, you could have 2 centers. Does that make sense?
If like the path was 6. Instead,
Sorry?
If instead it
If
was
the
6.
path were of length 5, if it had 5 edges, then the center would be one of 2 things. So, well, let's take an easier case. If the path had 4 vertices, which one is the center? This one or this one? Well, they're both centers. It doesn't matter which one you pick, but typically it's an edge, so you might as well pick both. All right. This also is a useful concept when you're working with trees and diameters. Yeah, thank you for reminding me. Okay. Any other questions? So what is left? What's the next piece to do?
What we tackled the intermediate island.
Right. So diameter is the intermediate island, because you're starting from the source, going to the intermediate island, and then to the destination. So that leaves us with what question?
For every node, we find the longest path
Longest path and
Within that tree.
source.
Right?
within that tree. Yeah.
Right. So compute, I'm going to call this R of V, which is the distance of the farthest vertex within that tree. Right? So how do we do this? So it turns out that a lot of the calculations we did earlier will help us again, and we can use that to do the processing. But any thoughts from the audience here on how to handle this? By the way, these trees were a little easy, so can I erase something here? Yeah, let me erase. I'm serious if I can work with this.
So we could use the same algorithm,
Okay.
but that might be too slow.
It's not a question of slow, both are linear time, so I don't care.
Well,
But how can the same algorithm work? Because remember, my vertex may not be on the diametric path. So finding the farthest vertex doesn't help me if I'm not on the diametric path.
Well, we could start at the vertex. We could have that be our root for the tree.
Sorry?
We could have that vertex be the root for the tree.
Which vertex?
Whichever one we have to start from.
Okay, right. So if I'm not using any of the things I've computed before, then it becomes expensive, because every time you tell me where to start, I'm going to have to do depth first search within that tree. You have to assume that the tree on each island is enormous, because remember, you could have 10 to the 5 vertices, right? So if it's going to be enormous, then we have to be a little bit careful on trying to recompute everything. So just because I gave you a different vertex this time, I'm gonna have to recompute everything and figure out how far away it is from the farthest vertex. I don't wanna do that, right? So I wanna pre-compute everything, and my question is, how do I pre-compute this without having to do depth first search from every vertex, right? That's really what I'd like to do. Give me a chance. Let's give the others a minute or two more. Okay, now that I've finished erasing slowly, have you thought this?
Maybe we do like DFS, and then we keep track of each path, and we record the nodes on each path,
Mm-hmm.
and then when we have a vertex, we look it up on like a table, right?
So I'm given a tree, arbitrary tree, I've just drawn one, right? And I could ask a question about anything. I could ask a question about that vertex, for instance.
We could use diameter.
Now, this vertex may not be on the diameter, and this is where the problem. If it is on the diametric path, then is it easy? How do I do this?
We can get a distance to the diameter and use the diameter.
Okay, distance to the diameter, and then pick the remainder on the diameter.
Yeah.
That's a good idea. So, so what is the diameter here? The diameter is probably going to be it's probably going to be something like that, right? Does that look like the diameter to you? So you're saying to go from the vertex to the diameter, and then not to take the shorter side, but to take the longer side, right? So but I need to pre-compute this. So what is it that I'm going to do? What is that pre-computation I need in order to figure out what is the R of V for this vertex V? Let me call this vertex V. Right? So based on what you're saying, I should start with the diametric path
Find
first.
some trees or something. Find some trees.
If something bothers me, let's based on what you just said, I should focus first on the diametric path, right? So let's say let's identify the diametric path. We know how to do this from the previous steps. There's my green diametric path. Can I figure out the R of V for everything on this diametric path? Okay, tell me. If this diametric path in this case has what? 1, 2, 3, 4, 5, 6, 7, 8 edges, right? How does that happen? Well, by the way, I should be using not 8, I should be using 9, which is the number of vertices on that diametric path, right? So therefore what? So forget about the rest of the tree, focus only on the diametric path. How should I figure out the R of V for each of the vertices on the diametric path? That's easy.
So for a given vertex, we figure out where is the parent inside the diametric path. In this case, will be that one, and we subtract everything else, the root and the other side, and we add that one.
Yeah, but you're telling me about how to handle this vertex.
Mhm.
I'm asking,
For any other, it applies.
I just want the diametric path. Tell me something simple first.
Okay.
How do I figure out this number for each of the vertices on the diametric path? That's easy, right?
Maybe
So
add
if the diameter is d,
Mhm.
where should I start?
maybe add vertices on both sides and pick what's the maximum.
You're not helping me. Remember, I've stripped down the tree. All I have is a green path. You should only see green. Yeah? And now my question is, if I know the length of my diametric path, how should I label each of the vertices on that diameter? Remember, what is R of V? It is the distance or the number of vertices on a path to the farthest vertex, right? So what is the number of vertices to the farthest point for that guy there?
It's the diameter.
The diameter. So this is going to be D, right?
D minus 1, D minus 2.
That's right. So if this is going to be D, so is this,
Yeah.
right?
Until you reach
This
the
one
center.
here should be D minus 1. This is D minus 2. So D minus 1, D minus 2. Then I do D minus 3, D minus 3, and this is D minus 4. Cool? That's going to be roughly half of D actually,
Center.
because it's the center. And that's the center of the vertex of the whole tree, in fact. And because there's only one vertex, there's only one center, right? So that's my center. Sorry, what did I do? This guy is my center, right? Okay, how does this help me? So now, based on your earlier thought, what's going to be the R value for that guy, for vertex V?
D minus 2 plus 1.
Path.
D minus 2 plus 1, right? So therefore, for everything else, I'm going to start from the diametric path and then essentially do breadth first search and label them. In fact, I can just do labeling from the center, which also is roughly the same thing. So if the center is labeled D minus 4, its neighbors are going to be labeled D minus 3. So I know that this guy also is going to be D minus 3, right? Their neighbors are going to become D minus 2. So this is going to be D minus 2. This is going to be D minus 2. This is going to be D minus 2. Clear? Then their neighbors are going to be D minus 1, D minus 1. What else am I missing here? D minus 1, D minus 1, D minus 1. And finally, this is going to have D, and this is going to have D. Hopefully I labeled everything there. You believe this? So what did I do? What were my steps? Can you summarize for me?
When you got the longest path,
So you find the diametric path.
points and then like.
So you label the things on that path by simply starting at the two ends and then working your way in. Find the center. In fact, we know how to find the center. The center is going to have a label of D over 2. If D is not an even number, it's going to be the ceiling of D over 2. So this guy's label is going to be D over 2C. That's for sure, because the diameter is of length D. Is that clear? So now you can kind of forget about the rest and just do breadth first search from there and simply label everything and you'll be done. Is that clear? So now we have labels that tell us, if you ever ask me about that vertex, well, its farthest guy is at length d. I just have to report. I don't even have to compute anything. Clear? Did that make sense? So a lot of it has to do with figuring out the center, and so this center thing is something that's quite important in trees, and many problems will sort of fall into place with that. If you know the center, you can figure out the diameter, you can figure out this value of farthest vertex in that tree, you can find all sorts of other, solve all sorts of other problems. So try and think about how you're going to find the center. Make sure you're clear about it. In fact, next time you go to a competition, take some code for this, and then work your way. Okay. So let me finish the rest of this code here. Identify the diametric path. Then the diametric path is going to connect two different leaves. They better be leaves on the tree, because otherwise you can go even further. The leaves of the tree are going to be labeled with D, which is the diameter, and then you work your way inside as D minus 1, D minus 2, D minus 3, until you stop at the center. The label of the center is going to be roughly D over 2, in this case ceiling. And then there may be two centers, so watch out, right? And then you essentially do breadth first search from there. Every new vertex you visit, you can label it one less, right?
Yeah.
One more, not one less. Yeah. So now you have all the pieces, and you're now ready to finish up the code. So this was a complex problem which involved lots of different pieces that had to come together. You needed to compute you needed first the connected components algorithm to figure out the three islands, because all you're given is the graph that's given to you as just a set of edges, right? From the set of edges, you have to figure out the connected components. You have to make sure that they are in three islands. Well, in this case, you don't need to, because you were told that the data is correct. Once you have the three islands, then your job was to find the diameter in each of the three islands. And for that, I sort of gave you a way to do this. Essentially, you first make the tree rooted, and then do a bottom-up processing. And as you do it, you can find the longest path that's completely in the subtree. And once you do that, you can figure out the diameter, because the diameter at every subtree, the largest one is simply going to be the diameter of the whole tree. And then once you have the diameter, you can figure out the diametric path. Once you have the diametric path, you can figure out the center. Once you figure out the center, you can do breadth first search from the center and compute R of V. And then you put all this together and you can solve the problem. Everything happens in linear time, so you don't ever have to worry about time complexity here. But that's only the processing. Then you have to write a separate piece of code for each of the queries. And for that, I told you that once you've done the pre-computation, each query only takes constant time. You just go and compute, figure out what R of U is, figure out what R of V is, and then add the diameter of the third tree. Okay? You got it all? Yes? This is a good place to stop, and if there are specific problems from the competition that you would like to hear, send me an email so that I'll prepare and not waste your time. Otherwise, I'd have to sit and figure out over here, which is not exactly the best use of your time or my time. I think there were a couple of really, really hard problems. You should try and understand them, because that's the only way for you to grow. So I'd say bring them here and we can talk about it, okay?